Hey guys, welcome. Yeah, so typically my example 0 is a proof of the theorem being presented. But here I've chosen example 1 as an introduction of Rolle's theorem before we do actual practice problems. And I'm going to make a video on example 0 should there be a demand for seeing the proof of Rolle's theorem. But yeah, additionally, notice that the main title for this is the mean value theorem. That's because Rolle's theorem is a special case of the mean value theorem. However, I have to introduce Rolle's theorem before the mean value theorem because in example 0 of the mean value theorem, we're going to prove the mean value theorem, and the proof of the mean value theorem relies on knowledge of Rolle's theorem. Yeah? Okay. I hope that wasn't all confusing and you kept track of everything I just said. I said it pretty fast. But yeah, Rolle's theorem has the same hypothesis as the mean value theorem, and that's this, which is we have a function f that is continuous on the closed interval ab and differentiable on the open interval ab. If that's the case, and we have that f of a is equal to f of b, then there must exist a c inside the interval ab such that f prime of c is equal to 0. Yeah, that's what Rolle's theorem says. Like, my kind of like very casual like way of summarizing what Rolle's theorem says is like, if you have a function that is continuous and smooth on an interval and it starts and ends on the same y value, that is like what goes up comes down in a smooth fashion, then you must have a horizontal tangent. But of course, your visual could look like the graph of this cubic. And so that's this. And so, it's not necessarily what goes up comes down. You could be like what goes down comes up. But yeah, if you're continuous and smooth, smooth means differentiable. And yes, it's a real math term, smooth. Yeah, but if you're continuous and smooth and you achieve the same y value at your start and end, then you must have a horizontal tangent. And that'd be like in this part, or like, like this, where you have the same y value, say here and here. And you're continuous and smooth in between, then you have a horizontal tangent. That's basically what Rolle's theorem says here. Yeah? Okay, cool. Now, if we just like narrow it down to like a very precise following of what's dictated here in this statement, then maybe like a parabola facing down might be like a better example. So consider this function g of x, which is this function here visually, right? Like this parabola has this graph, and obviously because parabolas are symmetric about their axis of symmetry, x equals minus b over 2a, there are a lot of x pairs where we achieve the same y value, right? For example, this 0 here and this 0 have the same y value, and clearly parabolas are continuous and smooth. And so like, then that means that we can follow Rolle's theorem to see that at the axis of symmetry, we must have a c. And in this case, c would be like minus b over 2a. And it'd be between, if we're using the zeros as a and b, between here and here, right? Or like we could do it between here and here, or whatever, right? But yeah, there's a c so that we have a horizontal tangent, meaning f prime of c is equal to 0. And again, for this parabola, the c would be at x equals minus b over 2a. Yeah, now just to make clear that the differentiability criteria is very important, not just the continuity criteria. Let's look at this example, which is, what if we considered this function? Well, this function would have this graph, right? And clearly, this function is not smooth everywhere, right? Because it has a sharp turning point right here, right? And that's called a cusp. So it's not differentiable here. And therefore, Rolle's theorem would not apply for this function if you pick an interval on either side of the vertex or the cusp. Yeah? Okay, cool. That's it for this intro to Rolle's theorem. And following videos, I'll do actual practice problems. The second problem will be a sophisticated one, so look out for those. And again, if there's enough demand for seeing the proof of Rolle's theorem, I'll prove it. Soon enough, I'll make videos on the mean value theorem. We'll start by proving the mean value theorem, which, as I said, will rely on Rolle's theorem. The proof of the mean value theorem relies on Rolle's theorem, yeah? Although Rolle's theorem is a consequence of the mean value theorem. Okay, all right. I hope this made sense, and I hope you enjoyed it, and keep watching. Take care.